The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so welcome back again to AO3. Today my plan is to continue the discussion of the two-string system, which we were working really hard last time, but we sort of ran out of time, so we didn't have time to enjoy what we have done, right? So today we are going to discuss all the outcome of that calculation. And also we will start to discuss more examples which can be described by the wave equation. Today we are going to talk about another example, which is sound wave. It's a very exciting topic. And afterward, we will start the discussion of electromagnetic waves. So this is the wave equation which we have been using. And over the last few lectures, we have been discussing two special kinds of solutions. The normal modes, which is actually standing waves in the end, which we identified, and the progressing wave solution, which is very powerful in describing the phenomena which we are familiar with. Last time, in the end of the lecture, we were discussing about an interesting example which involved two strings in the system. One is actually in the left-hand side have mass per unit length rho L equal to rho 1, and right-hand side one is thicker, and therefore the mass per unit length rho is larger, which is called rho 2. What we did last time is to assume that we have a progressing wave, which is actually going into this which is actually first initiated in the left-hand side string, and is going toward the boundary of the two systems, the more massive one and the less massive one, and see what is going to happen. And what we actually tried to describe last time is that we actually define incident wave described by this Fi function, transmitted wave Ft, and the refractive wave Fr. By using boundary conditions, which we described last time, we can conclude that there's a fixed relation between the three wave functions. What we actually concluded last time is that Fr is proportional to Fi, which is the incident wave function, by some constant which is called R. And what is R is, as we solved last time, is V2 minus V1 over V1 plus V2, which are the velocities of the first and second string. And the transmitted wave, Ft, is actually also proportional to the incident wave. And the coefficient, we call it tau to describe the amplitude of the transmitted wave. Okay? So what we actually can do is the following. So we actually discussed two examples last time, plugging in V1 and V2. And there are two more examples we can actually make use of this equation we obtained last time to discuss what would be the physics outcome of this kind of situation. So the first example which we can actually discuss is that, okay, now I have the string, as usual, connected to a wall, okay? So this time you can say, oh, wait a second. There's only one string now, right? But the last time we were solving two strings, right? But what I'm doing now is to treat the wall as if it's a string, okay? But this wall is really massive. Therefore, the rho L, or the mass per unit length, is really large, okay? Goes to infinity, okay? If that's the case, if you accept this idea, Okay, this is still a two-string system. Okay, then I can now go ahead and calculate what would be the velocity. The velocity v2 will goes to 0. Okay, then I can go ahead and plug into my equations, right? So we spent a lot of time in the last lecture to obtain those equations, and we will find that if I have v2 goes to 0, I have r equal to -1, and tau, which is actually related to the amplitude of the transmitted wave, is equal to 0, as you can see from this equation. Okay, what does that mean? That means once we solve that question, we also know what will be the outcome of this experiment, this physical situation. When we have a string attached to a wall and we have an incident wave, and as a function of time, what is going to happen afterward is that this wave is going to propagate and hit the wall and got refracted completely. Okay? The amplitude ratio is -1. Therefore, all the energy is refracted by the wall, okay, in this very highly idealized situation. Okay? So that's kind of interesting. The second example is also very interesting. So if you have a string attached to a massive ring, okay, and this ring can go up and down freely without any friction, okay? You can again say, no, this is again a single string system, right? But what I'm going to argue now is that, okay, there is another string which is so light, the mass per unit length is close to 0, okay? So it's actually the air, okay? If I do that, what is going to happen? The rho L is going to go to the limit of 0, right? Because the right-hand side, you almost cannot see it. And the v2, which is the velocity of the transmitted wave, goes to infinity. Okay? If that's the case, you can actually again plug into this equation we obtained, and you will conclude that r will be equal to 1. And the tau will be equal to 2. So what does that mean? This means that if you have this end, which is the open end, is attached to a ring which you can move up and down, then you get the refraction. The refraction, the amplitude of the refractive wave doesn't change because r is equal to 1, right? So it's still in the positive direction we define, but now it goes backward. Again, all the energy is actually refracted, as you can see from this equation, right? But the curious case is that the strange thing is that the tau is equal to 2. That's kind of strange, right? Tau is equal to what? Equal to 2. What does that mean? That means you are going to predict a transmitted wave with amplitude exactly 2 times of the incident wave, and it's going to be propagating in the right-hand side at the speed goes to infinity, okay? What does that mean? Does that mean the energy is not conserved? Have we found the cure of the energy crisis? Right? Because now actually I can actually take all those energy, okay, I can design this thing, right? Then this thing will bounce around all over the place, and it's going to emit energy, right? Oh my God, we solved all the problem. You should be really excited about it, right? No? But unfortunately, rho L goes to 0, right? So there's actually nothing oscillating out of this system, okay? So therefore, there's no additional energy radiated out of this system. Too bad, right? Go back to work. All right. So that's actually what we discussed last time, and I hope that complete the loop. And today, before we actually move to sound wave, I would like to also talk about very briefly harmonic progressing waves. Okay, so now you can see that a harmonic progressing wave looks really beautiful, as you can see here. And it can be described by a cosine kx minus omega t plus phi, right? Or you can actually, phi is actually the phase. And you can always write it in different forms. And since we have learned how to describe in general the progressing wave, this is just to remind you that, okay, there's no problem also to describe a harmonic progressing wave, okay? All right, so since we have learned about waves which involve oscillation in the transverse direction, okay? So basically we always say, okay, things are oscillating up and down in the case of string. Before I start the sound wave, there's a different kind of wave which we can also see very often in the daily life. It's called longitudinal waves, okay? For example, I can have a spring wave, okay? And I can actually, so imagine that I have a spring wave, and I can actually do this. I oscillate in the horizontal direction. Then that can produce displacement with respect to the equilibrium position. And this kind of behavior is like a density wave. We call it longitudinal waves, okay? This is actually exactly what is happening with sound wave. So what is actually sound wave? It's actually a collection of motion of air molecules. And they are actually oscillating back and forth. And we make use that to actually send energy all over the place, okay? And today we are going to discuss the sound wave. And by the way, just for simplicity, because drawing all those dots really take a lot of time, okay? So what we sometimes do is that, okay, we can now draw the pressure, the amplitude of the pressure, or the amplitude of the displacement of individual molecules in the discussion as a function of time. So if we draw the amplitude as a function of time or as a function of location, then it looks exactly the same as what we discussed before for the transverse direction waves, okay? So just some clarification. It's not like the molecules are going up and down. They are going back and forth, and it's just a matter of presenting the result, okay? So this is actually an example of a traveling wave in the longitudinal direction. And you can see that it is actually the density which is actually changing as a function of time. And as you can see, it's actually traveling at a fixed speed and going in the right direction of the blackboard. Okay. All right. So with those being said, we can actually get started with a concrete example. Okay. So I would like to discuss with you now a system which is like you have a tube. Okay, a tube with cross-section area A. So A is actually the area of the cross-section, and I can now wonder now the physics question I'm asking is what will be the behavior of the air inside this tube. So before I go ahead and solve this problem, I need to define and give you some more information about this tube and also the condition or say the environment this tube is living in. So the first information I would like to give you is that the pressure, the room pressure, is actually the P0 in this example. So the P0 is actually the room pressure. And I can now define a coordinate system. The x direction is actually in the horizontal direction, pointing to the right-hand side. And now I can actually try to describe a small uni volume inside the tube by the location x, and the width of this small volume, I call it delta x, okay? And if I go ahead and prepare this system, and at time t, there's something happening to this system. So now this unit length, unit volume I was discussing is get displaced with respect to the equilibrium position. So that means assuming that something happened at time equal to t, the left-hand side edge of the volume is shifted toward a positive direction, which is described by wave function psi x. And the position of the right-hand side edge of this volume is shifted to psi x plus delta x. Okay, so something happened to this system. Okay, we can also say that we can also describe this system, the pressure of this system, by P function. P of x is actually equal to P0, which is actually the room pressure. Okay, P0 is the baseline room pressure, plus some kind of displacement in pressure, psi p. Okay, so that will describe the pressure acting on the left-hand side edge of the small unit volume. And the right-hand side, you can also do the same thing. P of x plus delta x will be equal to P0 plus psi p, describing the displacement or how offset the pressure is as a function of x, but now evaluated at x plus delta x. Okay? So once we have all those elements defined, this is actually just a copy of what I have in the slide, and also some reminder here. And now we can actually calculate the motion of all the molecules in this volume, right? Because when I have pressure, I have displacement, right? Which is the displacement is described by psi, in position is described by psi. The change in pressure is described by psi p. And now I can go ahead and apply, for example, Newton's law, right? Then I can calculate what will be the acceleration, right, for this for all the molecules inside this volume, right? But wait a second. That sounds all great, but I don't know yet how to relate pressure and the volume, right? Because the pressure is actually expressed by psi p, and the volume is related to psi. I need to know what is actually the relation between pressure and the displacement, or pressure between psi, so that I can make progress, right? So that is actually the main discussion which I would like to do in this lecture. Okay? So given those information, I can now calculate what is actually the change in this little volume. So if I can calculate the change in volume, which is described by delta V. Okay? The delta V can be actually calculated by A, which is actually the area of the cross-section, times psi x plus delta x t minus psi x t. Right? So basically, just calculate how much the boundary is actually displaced. And if we always take very small amplitude approximation, okay, then basically this expression is roughly equal to A partial psi partial x times delta x, where the delta x is really very small. Okay, it's a very small volume I was talking about. And I can also calculate the pressure difference. What is the pressure difference? The pressure difference is between the pressure acting in the left-hand side edge and the pressure which is acting on the right-hand side edge, right? So I can now calculate pressure difference delta P. The delta P will be minus psi P x plus delta x T plus psi B x T, right? So basically, one is actually, the pressure is actually pushing the body in the right-hand side. The other one is actually pushing it in the left-hand side direction, right? Again, I can take very small delta x approximation. Then basically what you are going to get is minus partial psi p partial x delta x. OK, so we have prepared all those information about volume and the pressure. As I mentioned before, the big question which we would like to ask is, how do I relate pressure and the volume, right? So that I can make progress. If I can relate pressure and volume, then I can know what is the relation between psi p and the psi. Then I can actually make use of Newton's law. Then I can calculate the resulting equation of motion. Okay? So there are two possible interesting scenarios which we can relate temperature, relate pressure and the volume. The first one was proposed by Newton. Okay? Newton said that, okay, this is an interesting phenomena, and what, in my opinion, although you actually displace this volume, make the displacement for those molecules in the tube, but because the heat was conducted from one region to the other region, all those regions are connected to each other, and the speed of this heat transfer is so fast, it's really fast, like instant. This heat is actually transferred from one direction to the other, one position to the other position. Therefore, over the course of this evolution, the temperature should be unchanged. Okay, no matter what you do to this, the air inside the tube, the temperature should be unchanged because Newton thinks that the heat should be, the speed of the heat distribution is really, really fast, much faster than all those vibrations happening in the tube. Okay, if that is the case, then that means we can use ideal gas law. P times V is equal to nRT. I hope that you have learned this before in AO1 and AO2. If that's the case, that means, so all those things are constant because we assume that temperature is unchanged. Right? Therefore, this is actually, the right-hand side is actually a constant. Therefore, P times V will be some kind of constant. The V will be proportional to 1 over P. Okay? So that is actually the first idea which coming from Newton in order to relate pressure and the volume. Okay? The second idea is coming from Laplace. Laplace says that, okay, he has a different opinion on this matter. he thinks that this is actually an adiabatic process. Okay? What does that mean? That means the heat flow from the compressed region to the other region is really negligible because the oscillation is really fast and the transfer of the speed of the transfer of the heat is really slow compared to the time scale of the oscillation. Okay? Therefore, in Laplace's opinion, he thinks that the whole process is an adiabatic process. If that's the case, which I will show you later, okay, that means you will have this relation between pressure and the volume. P times V to the gamma. Gamma is actually related to the degrees of freedom of the molecule, okay, which we will discuss later in the class. This will be equal to a constant. Okay? So the very interesting thing of this lecture is that we are going to be able to test which one is correct. You will be able to see if Newton wins or Laplace wins. Okay, so as I mentioned before, one is actually assuming the heat transfer, the speed of the heat propagation is really, really much larger than the speed of the oscillation. The other viewpoint from Laplace is that the heat flow is actually really negligible compared to the oscillation we are talking about here. And now, as usual, I would like to have a vote now. How many of you support Newton's idea? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 15 of you vote for Newton. How many of you think Laplace is correct? How about the others? Okay, very good. So we have a majority of you support the idea of Laplace, and some of you actually support Newton, and we are going to see what is going to happen in the lecture today. Okay, so let's go ahead and apply these two ideas. Okay, so PV gamma equal to constant. So in the case of ideal gas law, gamma is equal to 1. Therefore, I just have to work on this functional form. And also later we will figure out what is gamma altogether. Okay, so let's consider only small vibration. Okay, small vibration means that I have psi p, which is actually from this definition, psi p is actually the change in pressure with respect to the room pressure, P0, okay? So psi p, assuming that's much, much smaller than P0, okay? And also, I assume that the change in volume, delta V, okay, which I calculated there, is much, much smaller than V0, which is actually the original volume of this little area, the original volume of this area I was working here, okay? All right, so that's the two assumptions, okay? Before I change the position of the boundary, okay, which is actually the upper graph, okay? If I change anything, I have P0, V0 gamma. This is equal to some constant C, okay? And gamma can be equal to 1 so that you have ideal gas law. After the vibration actually happened, after the walls are actually displaced from the equilibrium position, okay, what I'm going to get is I will have P plus delta P times V0 plus delta V to the gamma. This is equal to C. Okay? So based on those, actually I have already calculated delta P and delta V, right? Okay. So in this case, actually this delta P should be okay. This is actually not the delta P I was talking about there. So I should change it to delta P, right? Because that is actually the difference between the resulting pressure and the original pressure, right? It's not the difference between the left-hand side pressure and the right-hand side pressure, which is actually shown there, right? Okay. So this delta P, which I have already defined, is actually called psi P, okay? Therefore, I will rewrite this to be P plus psi P, okay? And I can now also copy this. You are going to get V0 plus delta V to the gamma, and this is equal to C. Okay? So as I mentioned before, I'm considering small vibration, right? Delta V is much, much smaller than V0. Therefore, this expression can be written as this should be P0. I'm making some mistake here, okay? This expression should be written as P0 plus psi P, okay? V0 to the gamma, 1 plus gamma delta V over V0, right? Because delta V is much, much smaller than V0, okay? Can everybody follow? Okay, so here I already take small vibration approximation, okay? And basically, I can now rewrite this thing. I just expand all those terms. Basically, I call this equation number 2, okay? Equation number 2 will become P0, V0 gamma, plus gamma delta V, V0 gamma to the minus 1, V0, right? Plus gamma psi P, V0 to the gamma, plus gamma delta V psi P, V0 gamma to the V0 to the gamma minus 1. Okay, so there's no magic. It's actually just expanding these terms. Then basically you are going to get 4 terms, right? And basically, if you do write down the equation number 2 explicitly, that is actually what you are going to get. Okay? So we are making progress, and we would like to simplify things. And you can quickly identify that, this term, P0, V0 to gamma, I know what is the value of that, right? That is actually the original situation, and that is actually equal to C. Okay? And let's take a look at also this term. this term is proportional to what? Proportional to delta V, which is actually a small, very small quantity, and proportional to psi p, which is another very small quantity. Okay? Therefore, taking a small vibration approximation, I will just simply ignore this term. Okay? Is everybody following? All right. So this term, this original term is equal to c, right? Based on this expression. So we start from the system before the vibration happened. After the vibration happened, there's a change in pressure. There's a change in delta V. But if you multiply PV to the gamma, this expression is still equal to C, some kind of constant. Okay? And then now I do small vibration approximation. And I drop the term, which is actually proportional to delta V times psi P. And basically what I get is that C is equal to C plus gamma delta P V0 gamma minus 1 P0 plus psi P V0 to the gamma. Okay? This term, these two constants cancel, right? And now I can actually move one of the terms to the left-hand side. Then basically what I'm going to get is psi P V0 to the gamma will be equal to minus gamma delta V gamma 0 gamma to the V0 V0 to the gamma minus 1 times P0. We can immediately cancel V0 to the gamma, right? Therefore, what we're going to get? I'm getting psi P will be equal to minus gamma P0 over V0 delta V. Okay? Everybody following? Okay, so this is actually the expression, and we also know what is actually delta V, right? Based on this expression, delta V is actually A partial psi partial x delta x, right? If you look at the upper board, which we actually just derived a moment ago, right? Therefore, I can replace delta V by that expression. Then basically what I get is psi P will be equal to minus gamma P0A delta x divided by V0 partial psi partial x. I'm just plugging in the expression for delta V to that equation. Okay, a lot of mathematics, but all of them should be pretty straightforward. You don't actually have to copy because all of them are in the lecture note. Okay? All right. So here, you can see that I can again simplify this expression. A is actually the cross-section of the tube, right? And delta x is actually the width in the x direction. So A times delta x is just V0, right? Oh, very good. Then I get this very simple expression, minus gamma P0 partial psi partial x. Okay. So we have achieved our goal to simplify the expression and find the relation between psi p and the psi. That's actually what originally we were hoping to do. And we have achieved that, and I call it equation number 3 here. Don't forget what is psi and psi p. Psi p is actually the amount of change in pressure, and the psi is actually the amount of displacement of the wall, okay, of the molecule in the volume. Okay? So now I'm really close to my solution, because now I can calculate the force acting on this little volume, right? Because now I know what is actually blood pressure, right? Okay, so what is actually F total? The F total is actually delta P, which is the difference in pressure from the left-hand side end compared to the right-hand side end, right? So that's actually what we calculated before. And that is A partial psi P partial X delta X. We also know what would be the mass, right? We know that the little mass in this volume, delta M, will be equal to rho, which is actually the density of the air, times A, which is the cross-section, times delta X. That will give you the area V0, right? So rho times A times delta X will be your delta M, okay? We are almost there. I have the N, I have the force. What kinds of law do I need to use to get my equation of motion? Newton's law, right? Newton's law. So F is equal to N times A, right? So therefore, I can now calculate M is actually, I can now plug in rho times A times delta X. What is A? A is actually psi double dot, right? That is actually describing the displacement, okay, with respect to the equilibrium position. And now I know this is equal to force, which is A times delta X partial psi P partial X. Okay? And you can see that both ends you have the delta X, right? So I can now cancel that. Both ends you have the A, so now I can cancel that. Then basically you get rho psi double prime. This is equal to partial psi P partial X. Okay, as from the beginning, we were talking about the relation between psi P, the displacement in pressure, and the psi, how much the molecules are displaced. And then we have the solution is actually here. If you assume the relation which is given by Newton or by Laplace, basically you can conclude that this will be equal to gamma P0 partial square psi P partial X squared. Okay? Okay? All right? And I can now put all the constants to the right-hand side, right? Basically, what you get is psi double prime. Okay, so here should be partial square psi partial X squared, right? Because I replace psi P by psi, right? Okay, and I must miss one. I must miss one negative sign somewhere. Where? Oh, this is actually there's a minus sign there, right? Yeah. On the left-hand side. Yeah, that's right. Okay. Yes, you are right. And the minus sign should belong there, right? Okay, so that actually, okay, sorry for that. So there should be a minus sign here, and there should be a minus sign here. And after I plug in equation number 3, then I get psi double prime equal to gamma P0 over rho partial square psi partial X squared. Okay? Any other problems you find? Not yet? Okay. Okay, so look at this equation. Oh my God, what is this equation? Wave equation, right? Again, wave equation. Okay? You can say that, I'm not surprised because this system is, used so many times. I have learned this so many times, but I'm still surprised that this is so identical to the physics which we have been studying for the strings for over the few lectures. Okay, so that's very nice. And now the question we haven't answered is that, okay, what is actually gamma, right? What is actually gamma? So gamma, in the case of a adiabatic process, okay, gamma is actually equal to alpha plus 1 minus alpha. And alpha is actually related to the number of degrees of freedom, right? So if you haven't learned this before, I have a complete proof of a adiabatic process. And this is actually coming from the first law of thermodynamics. And basically, you will be able to conclude that gamma will be equal to alpha plus 1 divided by alpha. And the value of alpha, the value you get for alpha is related to how many degrees of freedom you can actually have in this system. Okay? For example, if I have a system which is actually made of atomic gas, okay? So there's only one atom, right, in a molecule. And basically, you have 3 degrees of freedom, right? So you can move this thing in the horizontal direction. You can move this atom upside down or back and forth, right? So there are 3 degrees of freedoms. And if you calculate alpha, that will give you 3 over 2. And basically, if you calculate the gamma according to the equation, you are going to get 1.67. Okay? On the other hand, if you have diatomic gas, okay, that means you will have more degrees of freedom. So basically, you have not only the translational degrees of freedom, the 3 ones which are identical to the atomic gas, okay, you can also have 2 rotational degrees of freedom. So you can have these 2 atoms rotating like this. You can have that rotating like that, okay? The tricky thing is that there's 1 vibration degree of freedom, right? As we actually learned from the coupled equation before. But this one, very trickily, is not excited at all at low temperature. You have to go to really, really super high temperature so that this actually contribute to the overall degrees of freedom. So therefore, you have a total of available degrees of freedom of 5. And if you calculate the gamma, you basically will get 1.4. Okay? So let's now calculate what will be the resulting speed of light. So no, not speed of light, the speed of sound. Okay? So if the temperature remain unchanged, okay? If you take this equation here, this is a wave equation, right? Therefore, I know how to calculate the speed of sound, right? The speed of sound will be equal to, the Vp will be equal to square root of gamma p0 divided by rho, okay? So I have figured out the rho and the run pressure for you. So the P0 will be 10 to the 5 kilogram per ms squared. And the rho will be equal to 1.2. Rho is actually the density of the air, right? So it's actually 1.2 kilogram per meter cube, okay? If I have gamma equal to 1, which is the case for ideal gas law, temperature unchanged, and if I calculate the resulting speed of sound, you are going to get something like 389 meter per second. So that's the prediction from Newton, okay? And the second case, if we have, if we believe in what Laplace actually said, the heat flow is really, really negligible compared to the speed of the oscillation. Then we have, as we discussed last time, in the last slide, gamma will be equal to 1.4. Therefore, you will be able to calculate the resulting speed of sound, and that is actually 342. Okay? So those are the predictions. And what I'm going to do now is to really demonstrate that we can actually measure the speed of a sound in front of you. So the first thing which I need to do is to switch so that you can see the camera. Okay. And now I have a setup here. Basically, this setup is like the following. So basically, very similar to the setup we have here, but at one end, we actually have a speaker which produces sound wave. Okay, so this is actually what we have. This is the tube, and we have one end. There's a speaker attached to here, produce sound wave, and basically the amplitude will look like this. So basically, this will create some kind of standing wave inside the tube. And I have another device which is actually a microphone. A microphone is connected to this scope, which shows you the amplitude basically the amplitude measured by this microphone. Okay, and you will see that, if I move this as a function of position, you will see that the amplitude is changing, is getting smaller when it is actually hitting the note here. Okay, because here there's almost no oscillation in the air. Therefore, you will measure a very small signal at that position. And if you continue to move, then you will see that, I move away from the note. Therefore, I see some kind of maxima. Then I see that this amplitude is dropping again. Okay? If I continue, then you see that, again, this amplitude is increasing to a very large value. Then it decreases to a minima around the note. Okay? So what I'm going to do now is to measure the distance between notes. Okay? And since the sound waves which I actually put into the system have a frequency of, let me see. The frequency I put in is actually 1 kilohertz, right? And with the location of the note, I can know what will be the wavelength of the sound wave, right? So therefore, I can now measure the distance between the three notes. Then I will be able to measure the wavelengths. Then I will be able to know who is correct, okay? If Newton is correct or Laplace is correct. So let's do that. So let me find the first minimum. So the first minima is around 64 centimeters. Okay, and you can see that. Say stop when you see that it's reaching the minima again. Stop. Okay, very good. So this is actually the first node, the location of the first node, And I was trying to find the next note, right, so that I can actually read out the wavelength. Okay, now this will increase again. And reach stop. Is that the stop sign? Okay, very good. All right, so I get the value, which is actually 30 centimeter. Okay, so now I can calculate what would be the lambda. The lambda is actually 64 minus 30. Then what I get is 34 centimeter. Okay, and if I calculate the velocity, okay, the velocity of the sound wave, then basically I have f times lambda, and that will give you, okay, this is actually equal to 0.34 centimeter, right? So that will give you 340 meter per second. Oh my God, this is so close to the prediction of Laplace. First of all, this is amazing. Why? Because with this, looks really crappy thing, I can measure sound, speed of sound. Secondly, the measurement is really great. It matched within like 1%. You guys did a good job reading off, stopping me, right? Very nice. And finally, very unfortunately, people vote for Newton is wrong, okay? So what happened is the following. What happened is that the Newton actually assuming that the speed of the propagation of the heat is really fast. But actually that's not true, right? Because, for example, I'm standing here and heating up the air, okay? Or, in the last few lectures, I even heat up the air by some kind of fire in front of you. But you don't feel the heat, right? So the heat propagation is really not really fast compared to the speed of vibration. The vibration is really quick because it's actually vibrating up and down 1,000 times per second, right? So that means what is actually much more reasonable is actually to describe this process as adiabatic process, okay? So we will take a 5-minute break here so that we can take questions, and then we will come back at roughly 39. Okay, so welcome back, everybody. So we can see that we from the last so from the discussion we had before the break, we see that the sound wave can be described by something which we are now very familiar with, the wave equation, right? And also we know what is actually the speed of the sound, which is based on this wave equation. Basically, the speed of sound is actually equal to square root of gamma p0 and over rho, okay? So gamma is actually obtained from this discussion of how many degrees of freedom we have. So the first case we discussed is if you have a single atom which make your air, then basically the gamma is actually higher, okay? On the other hand, if you have diatomic gas, then the gamma is actually slightly smaller. It's actually 1.4, okay? So what will happen if I change the air in my lamp to monoatomic atom? So what is going to happen is that the speed of sound is going to be increased. The speed of sound will increase, and I have a fixed size of lamp. Right? I didn't increase the size of my lamp. Therefore, the frequency of my sound will what? Will increase, right? So how about we do that experiment and see if it works? So here I have a balloon here, which is full of helium, okay? And let me see if it works. I'm not sure if it will work, but let's see, cross the finger crossed, and see what happens. Now I'm going to do a major operation to replace all the air in my lung by this. Is my sound changed? No. Doesn't work. Let me do that again. That's a bit more aggressive. Did you hear any difference? No. Any difference? That's okay. Works now? Very good. Maybe we should use this sound. Maybe we should use that sound to go over all the lecture, right? Okay. It's a very dangerous experiment because you are replacing all the air in your lung, so you may choke, right? So that's okay. Fortunately, I survived this experiment, and hope you enjoy. So what happened is the following. So basically all the gamma become large, right? Therefore, the speed of sound in my lung become large. Therefore, the frequency of my sound increased, and you hear some really strange sound, right? Okay, very good. So before the end, I would like, okay, poor Newton. Before the end, I would like to discuss with you something which I hope I will not see that again in the exam, which I saw that before. So if I create a progressing wave, okay, in a single, okay, in a closed-end plus open-end tube, okay, this progressing wave is going to be propagating at the speed of what? Speed of what? Sound, yes. It's going to be propagating at the speed of sound, and you will reach the boundary, okay? The question is, will we see this? Will this progressing wave just simply leak out of the tube? Okay? How many of you think that's going to happen? Okay? I hope I will never see that again in the exam. This will never happen. Okay? Why? That means you have a super narrow collimated progressing wave going straight out of the tube, and that will not actually match the boundary conditions at the end of the tube, right? So that means basically, first of all, there will be no refraction, okay? That means all the energy is actually transferred outside of the world. And according to what we actually discussed before, what you will expect is that, okay, now you suddenly change to an environment which you have really very large volume. Therefore, it will be very difficult to change the pressure outside of the tube, right? Because what you are actually connected to is a reservoir of infinite number of molecules outside. It's going to be really hard to change the pressure, okay? Therefore, apparently this behavior doesn't match the boundary condition, and therefore what you should expect is something like this, which I can actually show you here. Okay, so in this case, you have both sides opened. What is going to happen is that at the boundary, actually, it's like the case of heating a wall, right? Because outside of the tube, you have really, really large volume, huge amount of air out of it, right? Therefore, it's like hitting a wall, and the amplitude of the progressing wave change sign and go back to the tube. And of course, this system is actually not perfect. Therefore, there can be some leaking out, some energy leak out of the tube, which is actually must be happening, right? Because we can actually blow the tube and then we can hear the sound. That is because some of the sound wave actually leak out of the tube. And this process will go over and over again. And this progressing wave is going to be going back and forth and like that, okay? So I hope that after this demonstration, everybody will expect that, okay, this will be not, the result will be like this progressing wave is going to be refracted because of the boundary condition and also change sign in terms of amplitude. Okay, so what we have learned today, so it's already close to the end. We have learned an example of a longitudinal wave, and basically longitudinal wave is actually in the form of density wave in the example which we covered today. And the mathematical description of the sound wave is going to be almost identical to what we have learned from the string case, which we actually discussed last time. And there are two boundary conditions which I would like to briefly discuss before we end the lecture today. So in the case of open end, as we discussed before, we can have a system which contains a closed end and the open end. What would be the boundary condition for a closed end? So the closed end have a wall here, right? Therefore, when you have your molecule, the air molecule oscillating back and forth, when they are actually close to the wall, they cannot vibrate, right? Why? Because it's hitting the wall, right? It cannot vibrate, so that actually the boundary condition at the closed end, where you have a wall closing the tube, is psi equal to 0. Okay? And on the other hand, if you have an open end, okay? If you have an open end, that means outside of the tube, the pressure is equal to what? Is equal to P0, the run pressure, okay? And you have so many stuff there, therefore it's not possible to actually change the pressure dramatically at the edge of the open end, okay? Therefore, what will be the condition? The psi p is actually, again, the displacement with respect to the run pressure will be equal to 0. Okay? Based on what we actually have learned from this expression, okay, sorry for that, I think it's hidden here. From this expression, psi p is equal to minus gamma P0 d psi dx, right? So psi p is proportional to partial psi, partial x, okay? Therefore, this boundary condition actually translates to partial psi, partial x equal to 0, okay? So this actually looks really familiar to you, right? Because in terms of psi, if you forget about this system, what those boundary conditions mean to you is exactly the same as you have some kind of a wall in the left-hand side, and it's connected to a string, and the right-hand side end of the string is connected to a massive ring, which can actually move up and down. These two systems, if you actually don't look at the detail, only look at the wave functions and the boundary conditions, they are identical. Okay, so that's actually the first lesson we learned from here. So when I talk about sound wave, or when you think about sound wave problem, there's nothing to be afraid anymore, because that's actually the same as what we have learned with wall and the string system. Okay, that's the first thing we learned. Secondly, that only works when I write my wave function in the form of psi. Okay, so now I can actually get the first normal mode will be like this. If I plot psi as a function of x, the second normal mode, doesn't surprise you, will look like this, etc., etc. If I plot psi as a function of x. On the other hand, we also know that psi p is proportional to the psi, partial psi, partial x, right? Therefore, you can also plot psi p as a function of x. Then what you are going to get is actually something like this. In the closed end, the psi p is actually reaching the maxima, right? Because it got the wall. Therefore, you can actually produce pressure on top of the wall, but you cannot move the position of all those molecules on top, in front of the wall, right? Therefore, that makes sense. You will see exactly in the opposite direction. If you plot the amplitude as a function of x, you see a picture which is almost like flipped. Okay. Of course, you can also do the same thing for the second one, and basically what you are going to get is something like this: the second normal mode, etc., etc. Okay. So be careful about the matching between the boundary condition obtained from the tube and the string wall system. They are identical. Open, close corresponds to open, close to corresponds to close. When you express your equation of motion in terms of psi, on the other hand, if you change that to psi p, then the relation is actually flipped. Okay? Thank you very much, and I hope you enjoyed the lecture today, and I will see you next week.